Okay, I guess we are going here. It's good to know. Um, Sorry, that first part of this lecture kind of stopped uh, abruptly. I realized it was time to go do something, and so it just stopped. So let's let's resume, and I want to go back to this concept that I started talking about, which is, R does different things depending on what kind of variable you provide for a function. So I'm not going to get into how it knows how to do that, but it's something that when you're programming a function, you can give it you can add on new abilities to functions like summary for new kinds of information. So let's see if we do like x. So I'm typing now is like x is equal to 1 from 1 to 10, and we say summary x. Well, it gives us those statistics. If we say summary and we say, I want to get summary information on chickweight, that original data set, it's going to go, oh, that's a data frame. So I know that for data frame, summaries means give me the summary of all the different columns in it. And as I was saying, I'm going to up. If you do summary on a model result, like the model result we created before, LM underscore chickweight, it tells you about what's in the model. Similarly, plot will give you the same kind of results. So if you just say like plot, it's going to give you different plots that relate to the behavior of the results of that model. So it gave us that box plot first that kind of blinked out of the way. Now it's giving us residuals versus fitted values. Now it's giving us a QQ plot, which sort of plots the quantiles of the residuals to let you know if they're normally distributed. If they fall in that line, then they're normally distributed. Otherwise, as you can see, they're not normally distributed. And some fitted values versus standardized residuals. And finally, the leverage. I'm not going to get into what the leverage is. But again, if you did plot X, it would just give you the values that are in that X variable. Whereas if you do it with the model result, it's going to give you, an idea of the fit and the model diagnostics, which is pretty cool, actually. I mean, my opinion. Okay, so now we're going to go on to the next summary, or the next step in this analysis, the regression analysis. Let's look at just a model for diet 1. Okay. And again, now we can look at, summary of LM diet 1, and we will find out that I put 3 M's in summary. There we go. And so, now let's look at the plot of that. So that's showing residuals the QQ plot, etc. Now, none of these models really look very good because all we've included is time. We haven't included the diet factor. Okay, so let's go on to, let's skip over these couple of lines because they're kind of redundant. Let's do a model that includes time and the and diet as a factor. So we're explicitly telling it here that diet is a factor variable. Okay. So now we have some ln, sorry. Okay, so now we have, we're looking at the results for the model, including both time and diet. And what do we see here? We can look at, the first thing you might look at is just the adjusted R squared right here, okay? So that's like the amount of the fraction of variance being explained, adjusted for the number of variables that you're using, okay? And let's look at the coefficients here in, and what we find are that, I'm sorry. What we find is that the intercept is statistically significant, time is statistically significant, and all three factor levels being considered here are also statistically significant. Now, why is factor one not here? Factor one's not there because that's considered to be the sort of the null case. So if the factor is diet one, then the predictive equation for this would be 10.9244 grams plus 8.7505 times time. For diet two, right, it's you add another 16 grams. For diet three, you add another 36 grams. And for diet four, you add 30 grams. So it's actually less. And you can see the t-values here, the standard errors, and the p-value of the overall relationship, the overall regression. Now I'm going to go back actually because I didn't talk very much about that first model. And so now I'm redefining LM chickweight diet as being equal to just the time. So now I'm asking, well, okay, well, what did time itself do without the other variables? And what we can see is, again, just using the, open that up for the moment. It explained, about 70% of variance, okay, as opposed to 74% of variance. So because we're explaining more variance and all of our factors here were statistically significant, then that suggests that there are statistically significant differences in the weight gain as a function of the diet, okay? And what you'll see actually is, though, even though the percent of variance explained, or fraction of variance explained, only went up from like 0.7 to 0.745, the F statistic there, look at that. So the F statistic went up from like 419 to 134.9. That was, it was actually a higher F statistic, and it went down for the using factors, but remember that we've changed our degrees of freedom in the model, 4 degrees of freedom versus 1. So that explains the difference in the F statistic. Let's do, I'm gonna go back and I'm gonna do this bring back in the diet as a factor, and then I'm going to do the plots again. So I want to see, okay, does this improve our residuals? Somewhat. I'm a little disturbed. I would be a little disturbed by the fact that we get this big residual for time 0. That the means for the smaller fitted values, so the lower weights, the average residual appears to be it's non-zero. So that actually is not a good sign of a model. I'm not very happy with that. And we still haven't actually done a great job with the residuals for the higher weights. So interesting. We haven't really improved the normalization, the normality of the residuals. So statistically, it's a better result, but it's not a model I'd be super happy with. So moving down, I'm going to bring back the text here. Let's see. We're going to use some of the techniques we used before, right? And we're going to make some plots that use the chickweights for. We're going to look at plots for chickweight 1 and chickweight diet 1 and chickweight diet 2 for just the diet 1 and diet 2 taken separately, and we'll make it nice in the graphics. So even just got an error here. Where did I? Oh, silly me. I did not define these up here. I skipped those. So here, I'm going to define those 2 models, right? And then I will redo and hopefully avoid getting an error. Okay, so that is telling us that even when we separate out the chicken weight for diet 1, the chicken weight for diet 2 as a function of time, that there's still a heck of a lot of variability in there. And the line in that case is the line that this AB line, okay, is creating the line, either in blue or in red. And because we're telling it to use the model results as the source for AB line, it's going to give us the regression line of time versus math. So these are the fitted values. Okay, well, that finishes up the introduction to our using chickweight, and that should assist you in your first lab using R.